Okay, so welcome everyone to our algebraic graph theory seminar. Today our speaker is Christopher van Bommel from the University of Manitoba, and he's going to tell us about pretty good state transfer and minimal polynomial.
Thank you, Sophia. So yes, today I'll be looking at pretty good state transfer and connections with minimal polynomials. So the setup here is we're looking at quantum walks on graphs, and the idea is looking for ways to transfer these quantum bits of information from one location to another. And sort of the naive approach there is we can swap the information held by 2 qubits. And so if we could implement a series of swaps, we could get the information held by a particular qubit wherever we want. The downside to this approach is it requires a large amount of control over the system. And so methods were considered for seeing how information would propagate through these systems naturally. And one of the simplest models was this idea of a chain of sites, so the spin chain, where you have Alice that starts with some information she's intending to send, and you allow the qubits to interact, and ideally after a specific length of time, and then Bob sees the qubit that Alice started with. So formally, we're setting up a continuous quantum walk. And so the idea is we set up this transition matrix or transition operator in terms of some matrix S that's related somehow to the graph we're working with. And it's this exponential function in terms of this matrix and in terms of time. And looking at graphs, what we're mainly considering here is the adjacency matrix. Other models are also possible here. There's a fair amount of work looking at the Laplacian as well, and various aspects of what I'm looking at today are largely applicable to both, but I'm still focusing mainly on how it applies in the adjacency case. So as I said, we're looking to get the information on these qubits from one location to another. So the overall goal is to achieve this idea of perfect state transfer. So we say a graph has perfect state transfer between 2 vertices A and B. If there's some time where if we apply the transition operator for that length of time to a state starting at vertex A, then we get out some state that's at vertex B with some scalar that represents the phase factor of the system. This can't be measured by the system, so we're going to ignore the phase factor and just treat any phase factor there as achieving perfect state transfer. One of the special cases is if we end up back at the vertex we started with, so we call this behavior periodic. And so we have a couple of examples for paths. So on a path of length 2, we have perfect state transfer between its 2 vertices at time pi/2, and then periodic at time pi. And for a path on 3 vertices between its end vertices, we get perfect state transfer on pi/√2. And then at pi times √2, it's periodic. So essentially, if you get perfect state transfer between 2 vertices and then let it run that time interval again, you'll get back to where you started. And unfortunately, we can't hope for this to work on longer paths. So Standel et al. In 2005 demonstrated with respect to the adjacency matrix, you can only get perfect state transfer on lengths 2 and 3. That was between the end vertices, and then this result was generalized to any pair of vertices on the path by Stevanovic and independently by Godsall. And that again, you can still only achieve this perfect state transfer on paths of length 2 or 3. So from there, if you're looking to transfer information over longer distances, there's some concession that'll have to be made. One example is this weighting based on the position along the path, and this comes from taking a quotient of the cubes and hypercubes. And in general, it was found you can achieve weightings that give perfect state transfer by predetermining the eigenvalues you want that satisfy specific conditions, and then solving the inverse eigenvalue problem you get. Some work has also been done just looking at adding loops to the vertices. So for the path, this is a negative. You can't achieve perfect state transfer between the endpoints of a path of length at least 4, no matter what loops you add to the graph. But for different sorts of graphs, so if you have a pair of vertices that have a common neighborhood and are not adjacent, then there's some loops that can be added to the graph to achieve perfect state transfer. And these results are due to Kempton, Lipner, and Yao. Alternatively to modifying the graph, we can relax our requirement on the state transfer itself. And so rather than requiring that we get exactly the same information out on the other end, we can say that we've become close enough. And what does that mean? It means that no matter how close we want to come, there's some time interval we can allow the system to run that we get within that probability of transfer. And so as an example, we can see this phenomenon on a path of length 4, where there's specific times where we're approaching this line of perfect transfer at 1, but we're not actually hitting it. And so if we look at pretty good state transfer on paths for between the end vertices, this was characterized by Godsall, Kirkland, Severini, and Smith. And you're looking for the length of the path to be 1 less than either a power of 2, a prime, or twice the prime. And if you get pretty good state transfer between the end vertices, then you get it between pairs of vertices that are equidistant from each end. And then looking at internal vertices of paths, so this is relevant when you don't have a pretty good state transfer between the end vertices, but you can still sometimes get transfer between some of the internal vertices. So Gabriel, Crystal, and I investigated this problem and found this family where the length of the path is a power of 2 times a prime minus 1, so sort of generalizing that idea of a prime or twice a prime. And the vertices, the index on the vertices, if we think of labeling the path from 1 to n, they had to be a multiple of 2 to the t minus 1. And then later on, I was able to show that that's the only additional family on paths that gives you pretty good state transfer, and we can rule out the possibility of pretty good state transfer on internal vertices in other lengths. So some other families where pretty good state transfer has been considered is double stars. So this is by Fan and Godsell. So the number of leaves on each end can vary. And so for any set of values there, you can't have perfect state transfer. But if you have 2 leaves on one end, and as long as you don't have 2 leaves on the other end as well, then you can get pretty good state transfer between those 2 leaves. And for larger stars, if they're symmetric, you can get pretty good state transfer as long as the number of leaves meets this particular number theory condition. If we add a vertex to the middle, we have this idea of one sum of stars, and this was investigated by Ho, Gu, and Tong. And again, there's no perfect state transfer here, but there is a pretty good state transfer, again, in the symmetric case where you have the same number of leaves on each end, and the 2 stems have pretty good state transfer. And then sort of the trivial case where you have 1 leaf on each end, and so you've reduced to a path on 5 vertices. We've already seen that has pretty good state transfer. There's a method of constructing examples with pretty good state transfer using Cartesian products. This was investigated by Pal and Bhattacharya. And the idea is if you have some graph with a periodic vertex and the second graph that has a perfect state transfer between 2 vertices, as long as the times at which this happen are rationally independent, then waiting long enough, those 2 occurrences will come close enough together that you can achieve pretty good state transfer between the corresponding pairs. And they observe that this allows the construction of a graph that has pretty good state transfer from a particular vertex to 2 different vertices. So this top left vertex can have pretty good state transfer to either the red vertex on the right or the blue vertex on the bottom, just at different times. And a few other examples of pretty good state transfer that I'll quickly mention are for circulant graphs. I won't go into the details on that. And additionally, dihedral graphs. We can again consider this concession of introducing edge weights or loops. So in this case, potentials or loops. And Kempton, Lipner, and Yao showed there's pretty good state transfer on the path for some choice of potential. So this allows us to not worry about what the length of the path is. We can always find a choice of potential there that'll allow pretty good state transfer to be achieved. And this was part of a more general result for graphs having an involution, so some automorphism of the graph that has order 2. And so if the automorphism fixes vertices or edges, then there's some potential that allows you to get pretty good state transfer. This sort of weighting was also used to achieve state transfer on strongly regular graphs. So for a strongly regular graph, we have a k-regular graph that's not empty or complete. The adjacent vertices have A neighbors in common, and the non-adjacent vertices have C neighbors in common. And this is a graph with 3 distinct eigenvalues. And we consider weighting one of the edges or possibly non-edges between a pair of vertices and adding loops to the ends of that weighted edge. And with that weighting, there exist weightings to be made as shown by Godzelgo, Kempton, and Lipner that allow perfect state transfer to be achieved under certain conditions. And for all of these strongly regular graphs, there's weightings that can achieve pretty good state transfer. And there may be a couple other classes out there, but largely this is the examples we have for pretty good state transfer. So if we look at some tools for investigating this problem, we'll be dealing with the spectral decomposition. Which is break down the adjacency matrix of a graph into its projection onto its eigenspaces. And this allows us to simplify the computation of the transition matrix. Rather than taking the exponential of our adjacency matrix, we just need to take exponentials of the eigenvalues and then multiply against these projections. And a useful tool for considering pretty good state transfer is this notion of strongly cospectral vertices. So first of all, 2 vertices are cospectral. If looking at this spectral decomposition, if we look at the diagonal entries corresponding to those 2 vertices, then they should be equal across the different projections. And this is equivalent to the graph without x or the graph without y having the same characteristic polynomial. And then two vertices are parallel if the vectors we get corresponding to each of these vertices for each of the projections are parallel. And then strongly cospectral. In one formulation, we can show this combines these two notions. What we say is that the vectors we get are either equal or opposite. And another way of verifying strongly cospectral that arises is if we have, that should be eigenvector. If we look at any of the eigenvectors, then the entries corresponding to vertices x and y should always be it. So we'll be looking at this idea of minimal polynomials, and we want to take minimal polynomials of the adjacency matrix relative to some vector. So this will be the smallest degree monic polynomial. So if we evaluate it at the adjacency matrix and multiply by the vector, we get 0. And so the ones we're interested in is if we're considering pretty good state transfer between two vertices x and y. The relevant minimal polynomials are those for the characteristic vector at x plus the characteristic vector at y, and the characteristic vector at x minus the characteristic vector at y. So we'll call these px and p plus and p minus. And when x and y are cospectral, these polynomials are factors of the characteristic polynomial with and then there's some extra term left over, which represents eigenvectors that are 0 on both the vertices. And if x and y are strongly cospectral, then p plus and p minus should have no common factors. And this approach for considering pretty good state transfer was investigated by Eisenberg, Kempton, and Lipner. One of the main ways of characterizing pretty good state transfer is this lemma based on Kroneker's theorem that was demonstrated by multiple sets of authors. So to get pretty good state transfer, the two vertices have to be strongly cospectral. And you have this condition on basically how dependent the eigenvalues can be on each other. So there's this idea that if you have integers, so that this linear combination of eigenvalues goes to 0, then the two sides, the two sets of coefficients that correspond to p plus and p minus, the sums of the coefficients there both have to be even. And so looking at minimal polynomials, Eisenberg, Kempton, and Lipner derived a condition based on p plus and p minus being irreducible. And this condition on the ratio of the trace of the coefficient of the sum of the roots of the polynomial or negative the coefficient of the second largest power. And we want these two ratios to not be equal. And that allows us to determine that there's pretty good state transfer between X and Y. And so their main application of this result is to show for adding potentials, that the polynomials p plus and p minus can be forced to be irreducible for some choice of potential, and that allows us to essentially start with any graph with cospectral vertices, change them to be strongly cospectral, and achieve pretty good state transfer. I've looked into this condition for unweighted graphs, and I've found some examples there that satisfy the conditions on this theorem. So some of the smaller examples we've seen before because they just end up as paths, but these examples are based on involutions. So we map the top row of vertices to the bottom row of vertices. And so any pair of vertices in the same column can achieve pretty good state transfer. And then a couple more examples for 8 vertex graphs. For pretty good state transfer on involutions, there's an earlier paper from Kempton, Lipner, and Yao that covers some of the cases that the previous result doesn't. So if you have an involution that doesn't fix any vertices or edges, then if the number of vertices is divisible by 4, and you have some condition on how the roots of the two polynomials can interact, then you can achieve pretty good state transfer. And if you're in the 2 mod 4 case, and all of your eigenvectors are supported on the vertices you're interested in, then you won't be able to achieve pretty good state transfer. And we'll see an extension of this second idea shortly. So thinking about the main result, there's essentially 2 parts. There's the ratio of the trace and the degree, and there's the fact that the minimal polynomials have to be irreducible. And we certainly can't just remove the irreducibility condition if we think of a path on 8 vertices. The 2 polynomials, p plus and p minus each factor, they do meet this condition that the ratios aren't equal, but we have seen that we cannot get pretty good state transfer in this case. The other side of that, we can consider what happens if the ratios are equal. So here we have essentially the wheel on 5 vertices, so center vertex with attached to all vertices of C4. And so we can determine p plus and p minus in this case, work out the eigenvalues, and if we use this lemma that characterizes pretty good state transfer, we can find a combination that breaks it. So if we set if we give a coefficient for each of the p plus eigenvalues of -1 and the p minus eigenvalue of 3, then we satisfy the two equalities, but we've got the sum of the coefficients is odd in each case. So that rules out pretty good state transfer here. And so this is part of this is an example of a case that can be ruled out. So if we have these, it's not even that we need p plus and p minus to be odd degree, but if they each have a factor that's odd degree, and if we look at the ratio on those factors, we find that they're equal, then using that sort of approach, we can show that you can't demonstrate pretty good state transfer in this case. And then there's a more complicated version that uses more of the factors that still allows us to rule out pretty good state transfer. So here we're looking at the double star with two leaves on each side. And again, we can find coefficients that satisfy the equations of the pretty good state transfer characterization, but have odd sums. So that rules out the possibility of pretty good state transfer here. And the idea here is if you can break one of p plus and p minus into a couple factors and find a factor in the other, you want a factor with odd degree, a factor with odd trace, and then to satisfy that this combination of trace and degree is odd, that gives us the structure to form those coefficients that rule out pretty good state transfer. So that leads us to question, is there anything outside those cases? Well, between those three results, we still actually haven't dealt with a path on three vertices. We know there's pretty good state transfer. In fact, there's perfect state transfer, but it has this, the trace of both minimal polynomials is 0, so the ratio ends up being equal, and we don't have these odd factors we can find. And that's a bit of a trivial example, and maybe if it was just that one, we could leave it at that, but there's more. So we've also seen the double star with one leaf and two leaves has pretty good state transfer. Again, we get these irreducible polynomials where the ratios with the trace and degree are equal, but we don't have these odd factors we can find, so it doesn't rule it out either. So I've recently been looking at these algebraic conjugates to consider what these rational combinations of the roots of these polynomials can come out to. So I was looking at a paper of Devicus, and a couple of results that I'll be using is if you have two algebraic conjugates and you want some combination of them to be rational, or have or have low degree in general, then essentially you have to either add them or subtract them. You can't have more varied combinations of the two of them. And then the second result here is if you have a combination of algebraic conjugates, so roots of some polynomial, and one of the coefficients essentially dominates the others, so it's equal to or greater than the sum of the others, considering the absolute values, then that combination won't be rational. And those results are enough if we have an irreducible polynomial degree 4, and we look at combinations where the sum of the coefficients is odd, that will rule out that this combination can be rational. And so that's helpful for finding additional examples of pretty good state transfer. In the interest of time, I'll omit the proof. So the idea here is if you have low degree irreducible polynomials, and I haven't seen yet how to go to higher degree ones, but I'm hopeful that there are, it seems likely that it would lead to other examples of pretty good state transfer as well. But if you have some conditions here, you'll achieve pretty good state transfer. So that gives us a couple more examples that fall into this idea. And generally the ones I've found so far have p minus just being x. And so we have a few examples. Some of them can be modified. So the bottom left is K23, and it doesn't make, that can be K2n in general. And we'd still get pretty good state transfer between the two vertices on one side of. Just want to wrap up briefly with another side of the question I've been considering, and that's a pretty good state transfer on modified paths. Chen, Moreau, and Feder investigated this idea of taking a path and adding new vertices to the third vertex and third from last vertex and weighting those new edges. And with this weight proportional to the square root of the length, they're getting increasing probabilities of essentially almost fully transferring the state. And part of what I'm questioning here is, well, is this actually an example of pretty good state transfer, or are the probabilities still bounded? They're just getting closer to 1 as we increase the length. And so this is coming from using these tools we've seen so far, so we can find characteristic polynomials for these modified paths, which essentially break down to being combinations of characteristic polynomials of standard paths. And if we look at the case where we're weighting by a transcendental, then the factors we could possibly get out of these minimal polynomials take particular forms that have to come from this common factor of the part without the weight W and the part with the weight W, or in some extreme case, this bit in the brackets might be a difference of squares and might be factorable in that sense. So with an unmodified path, we always had that the end vertices were strongly cospectral, and if we modify it the wrong way, we can lose that property. So here's an example on a path of length 9 where we attach at vertices 4 and 6. And if we look at the eigenspace for the eigenvalue 0, we get these 3 eigenvectors and they don't meet this property where the end vertices, which are actually the second column and second last column, they don't have this property that they're equal or opposite. And so that rules them out of being strongly cospectral. And this idea holds in general. If you're adding your new vertices to an even index, then you're not going to have strong cospectrality there. And so you can't hope to have pretty good state transfer. If we look at some of the odd cases, sometimes these minimal polynomials are going to be irreducible. So for example, in this bottom case where we have 10 vertices, there's no common factors to pull out. In the top case where we have 8 vertices, we can see a common factor of x minus 1 and a common factor of x plus 1. And so that'll give us different cases to consider there. So sort of coming back to those results, the case where the polynomials we get are irreducible leads us back to that original result with irreducible polynomials and the ratio not being equal, and avoiding that common factor occurs if the length plus 1 and the index we're attaching the new vertices are coprime. And the case I know that pretty good state transfer won't be achieved is matching this idea of pulling out the 3 different polynomials, and that can happen if m is odd, the length of the path is even, but it's not divisible by 4. And there's this prime factor that's congruent to 3 mod 4. And this gives us enough structure to pull out these polynomial factors, that the 3 of them that rule out pretty good state transfer. So just thinking about where this is going, hoping to have a full characterization in terms of the minimal polynomials for when pretty good state transfer can be achieved. There's still some missing cases there. That'll hopefully help with the characterization of these modified paths, since there's still several cases that haven't been considered there. And one of the questions that frequently crops up with pretty good state transfer is, okay, yes, you can achieve transfer with arbitrary success, but really how long does that take? And so looking at what sort of time scales are required here and do different weightings or different modifications lead to better or worse timescales. And another question that's been floating around is resolving when perfect state transfer or pretty good state transfer can occur on trees. And thank you very much, everyone.
Thanks, Christopher. Do we have any questions?
I have a kind of vague question. I want to say thanks for an interesting talk, but I'm curious, can you say something about what about this problem you find particularly interesting or appealing? You gave a nice overview, but I didn't get a sense of, kind of what brought you into it.
I think these questions where you have some problem, but it brings in results from other areas to pull it together are quite interesting. So we saw a couple of places where you can get pretty good state transfer really depends on the number theory, like how the numbers divide and what factors they have, and just bringing these different tools together that may or may not always be linked has been quite interesting in these sorts of problems.